elaborate on this. You create something up on the free store with new, and you get given a pointer. Somebody has to call delete on that pointer to give that memory back to the free store. In its simplest form, you have the beginning of a function, new, employee, do something with the employee pointer. At the end of the function, delete the employee pointer. But that's kind of pointless. You could just use a local variable. Why did you bother newing something up? Probably this pointer is going to go into a member variable of a class and you need to keep track and call delete when everybody's done. But along the way, some strange things can happen. Like someone could copy your pointer. And maybe they still have the copy when you think you're done with the original pointer. If you delete the pointer, the copy they have is pointing to memory that's not available for use. That's a blow up your application situation. Or if you keep your pointer in some local variable that goes out of scope and you don't have the pointer anymore to call delete with. Manual memory management is flat out hard. You can delete things too soon and then other code tries to use them and they're not there. You can delete twice and you can never delete, which is a memory leak. It's actually quite difficult. The good news is you almost never have to do it. Library writers have solved this problem for you. But to convince you that you want to use what the library writers have written, I'm going to show you how to do it yourself by hand so that you know what you're being saved and so that you maybe understand where some of the eye-rolling and stories have come from people who say, oh my gosh, C++, pointers, new, delete, memory leaks, you have to do it yourself by hand. I'll show you what they're talking about, but the whole time I'm doing it, I want you to remember, you probably don't have to do this, okay? So I'm going to teach you something called the rule of three. The rule of three says, if you write a destructor that really does something bad, because remember, delete doesn't just give the memory back, it also runs the destructor. You should also write a copy constructor and a copy assignment operator. I have a demo for you in which we're going to deliberately trigger all kinds of chaos and mayhem and slowly bring it under control by writing the big three: copy constructor, copy assignment operator. I'm going to start by showing you manual memory management when there aren't member variables, when you're just working with local storage that has pointers to something on the free store, and those pointers can go out of scope when your local function ends. That will be the start of our complications. Here I'm using a class called Resource. It's very simple. It just has a string in it. It has a constructor that takes a string, and I'll show you the code in a second, but it sticks it in this variable, not surprisingly, and a destructor, and it has a get name that gives you that string back. The constructor does initialize the string, as I mentioned, and it also prints something out, and the destructor prints something out, so we can do some life cycle tracking. First, I'm going to create a resource locally on the stack, as it were, call its get name using the dot notation, and then when we hit this brace, it'll go out of scope, and you'll see it go out of scope in the destructor run. Just a reminder of how local variables go out of scope when they hit their close brace. Then I'm going to create a resource on the free store using operator new. That gives me back a resource pointer, which I'm putting in this variable pResource. And I'm going to use the arrow notation to call this member function getName on pResource. Then I'm going to start doing bad things. The first bad thing I'm going to do is I'm going to make a copy of pResource, put it in this other resource pointer called p2. And I'll call getName on that to prove it's still working. And then I'll use delete to delete pResource. And so the first thing I'm going to do is try to use a pointer that I just called delete on, let you see what happens. Then I'm going to set that to null pointer and delete it again. And then I'm going to try calling p2. p2 is pointing to some memory on which delete has already been run. This is quite a collection of badness. What's going to happen is I'm going to run it, it's going to blow up, we'll look at the error, I'll comment out the bad line, it will go like one line further and get the error again, and so on. So let's begin. Free store has stopped working. How far did we get before we stopped working? Well, you notice we constructed the local and then destructed it, and we constructed the created with new, and then we destructed it. In other words, we got past here, It was no problem trying to get these values from P2 or PResource into these local strings. We deleted this PResource. That caused the destructor to print out that it had cleaned it up. And then when we tried to do this, it blew up. And I can prove that quickly with the debugger. I'll put the breakpoint right here and just run to the breakpoint. Okay, we're fine to here. There's some very small output there. And when I step over, this is where we blow up. When you do this under the debugger, the error messages are a little different. You get unhandled exception, bad alloc, can be a little harder to read, so I've been trying not to get it to blow up under the debugger, but that's where we were when it blew up. I'm going to stop debugging and close the random piece of the standard library that we ended up in. We blew up because of this line, of trying to call getName on PResource when PResource has been deleted. Let's do that, and I'll run it again. Oh, this is quite bad, right? We got into a destructor, obviously. It's printing out destructing, but when it tried to get hold of the name, that's when it blew up. I happen to know which of these two deletes caused the problem. And again, I can show you which by using the debugger. Okay, we're fine till here. We set PResource to a null pointer. We try to delete a null pointer. That's harmless. You can do that all you want. Delete basically says, is it already null pointer? Okay, never mind. It returns. Nothing bad happens. But when we go to delete P2, that's when the bad thing happens. And it's simply that P2 is pointing to memory that's already been cleaned up. And calling delete on it again, it is bad. Now, just to prove that it's not the copy that's the problem, I'm going to comment out this line that sets PResource to null pointer. And now if I run, let's move the breakpoint. This line's going to make it go boom. And it does. Deleting something that's already been deleted is a bad and dangerous thing to do. If you set it to null pointer, it's safe. Here, P2 points to the same place that PResource points to, and so once you've deleted PResource, trying to delete P2 is exactly the same as trying to delete PResource twice. You might think that you would never make these mistakes, trying to talk to an object after you've already deleted it, deleting it twice, those sorts of things. All right, I'll believe that. Let's comment out all this weirdness and just run this to prove that we are currently a balanced application. We construct the local one on the stack and then destruct it when it goes out of scope. We construct the free store one by calling new, and it gets deleted exactly once. Nobody blows up. Everybody's happy. Who said this memory management stuff was tough? I don't know what you're talking about. Well, I tell you what. Let's just do something relatively mild here. I'm going to make myself an integer, and I'm going to make a test to see if that integer is 3, and you can tell that it is. And I'm going to return from my function early, if it's 3. Could happen. Here's what's going to happen. We will call new, and then we will return, and we will never delete it. If I run this, there's no error, there's no blowing up, but do you see what happened? We constructed and destructed local, but we only constructed the created with new. We never destructed it. That's a memory leak. Now this application is about to end, so, what harm did the memory leak do? But in a real application, if this wasn't my main, but a function that processed something, and if resource was 1,000 bytes, 10,000 bytes, could easily be, and I leak that many bytes out of the free store, sooner or later when another part of my code tries to get memory from the free store, it's going to be told there isn't any. And that's when the application hangs, and while back in the day we used to have to reboot the whole machine, but you're still at least going to have to end task your application. Memory leaks can be really crippling. And memory leaks happen when you don't delete something. We have code to delete it, but that code doesn't execute because we bailed out in the middle of the function. And occasionally in this material I refer to exceptions. You may say, I'm never going to write return in the middle of a function. Exceptions can do that to you. So you have to think about how can you write your code in such a way that it works even if someone bails out in the middle of the function. Now here, my pointers, PResource, P2, they're local variables. They're not going anywhere. They don't have a long life themselves, although they point to long-lived things out on the free store. Things get a little weirder when you put a pointer as a member variable of a class. Here, I'm working with the person class again, but this person is a little bit changed from the person that's been kicking around for so long. I want to show you how it looks. Person, in addition to a first name, a last name, and an arbitrary number, now has a resource pointer. When I construct a person, I set their resource pointer to null pointer. Now this particular idiom is one that you would use if something is optional. You might have a resource or you might not. When you don't have a resource, the pointer is null pointer. When you do have a resource, the pointer points to the one resource that you have. So we have a member variable in person called AddResource. And this member function creates a new resource and puts the resulting pointer into this member variable PResource. Here I make myself a local person. I'm going to call AddResource, and then I guess my work is done. Let's see what happens. Constructing resource for Kate Gregory, and we're done. So this is a memory leak. We never destructed it. That was foolish. Now there's nothing wrong with allocating my resource out on the free store with new. In fact, it's the only way that I can get a resource that lives longer than this function. If I just created some local variable and then said PResource is equal to the address of R, the minute we come out of scope here, R goes out of scope, it's cleaned up, and PResource is now pointing to something that's been cleaned up. And you saw how badly that worked out in the other demo where trying to talk to something that's already been cleaned up causes crashing. You can't do this. You want a resource that lives out on the free store so that it lives longer than AddResource function runs. So the solution to the memory leak is there needs to be a delete somewhere. So we can go into the destructor for person and say clean up that PResource pointer. That's all. I don't need to check to see if it's okay to delete it or not because it started out as null pointer, and as I mentioned, you can call delete on null pointer and it's harmless. So I'll just call delete on it. If it's null pointer, nothing will happen, but if it was set with AddResource, it'll call delete on. Okay, let's run this. One constructing, one destructing. We're back in balance. Hooray. That works, but only because the person who wrote the main hasn't done anything bad yet. What I want to do is to write a person class that is thoroughly robust to people doing, well, bad's not the right word, ordinary stuff that happens to be dangerous, running with scissors, as it were. So here's one thing a person might do. They might call AddResource twice. Probably not on consecutive lines like this, but if it's a big complicated application with lots of code passed through and it happens to come across the AddResource call more than once, what is my app going to do about that? And here, to make it easier to tell them apart, let's call SetName so that the resources, they build their name from the name of the person, and we'll be able to tell them apart. I'll run these. And we're back to having a memory leak. We constructed the first one for Kate, then we constructed a second one for Kate 2, and we ended up only cleaning up the one for Kate 2. The one for Kate is just sitting out there still on the free store forever, causing a memory leak. Why? Because we gave this the name AddResource, and that's what it does. It just adds another resource out on the free store for us. It should probably have a different name. I'm going to leave its name alone, but I'm going to fix its code. If there is an existing P resource already, we need to get rid of it, clean it up. So I'm just going to copy this line from the destructor. Again, if P resource is null pointer, this is harmless, but if there is a P resource, this will clean it up, and then we'll new up a fresh one. Let's test it. Much better, we're back in balance. We construct the Kate, clean it up, construct the Kate 2, and eventually clean that up when the person object goes out of scope and its destructor cleans up its resource. Okay, we're starting to create a person class that is managing this resource appropriately. But again, we need to be robust to the sorts of things that people might do when they're consuming our person class. So here's another behavior that maybe you didn't count on. I am making a copy of Kate and putting it in another person object called Kate2. The compiler will actually construct a Kate2 object and copy each member variable over from Kate to Kate2. That's the default behavior. So the first name will get copied over, the last name, the arbitrary number, and the P resource pointer. And then you know what's going to happen? When we hit this close brace right here, this person object's going to go out of scope, and this person object is going to go out of scope. The first one who goes out of scope will delete P resource. That's great. Clean up the free store, life is good. Then the other one will go out of scope and will also attempt to clean up the very same thing. It's just like over here in this example where we deleted P resource and then we deleted the copy of it, P2. Here on code you don't see, when Kate and Kate2 go out of scope, they will each try to delete their own copy of that pointer. The second one, well, it's not going to be good. There we go. We're tucking along nicely, but we have that extra destructing, and it's blown up. Exactly the same problem. We're trying to delete something twice. So what can we do to protect ourselves against somebody doing this? You could say, no copying people. The person class is not for copying. And there's even a way that you can get the compiler to help you with that. But I'm going to guess that that's probably not a rule you want to impose. After all, it would make it impossible to pass it to a function by value, for example. We have to teach the system how to copy person objects safely. And we do that by writing what's called a copy constructor. I'm going to go into person, and here, with the existing constructor that we already have, I'm going to add another constructor. You know it's a constructor, it doesn't have a return type, and it takes a const person reference P. Now I need to implement my copy constructor. I'm going to copy this one, but my parameters is not all these individual bits and pieces. It's a const person reference P. And I'm going to initialize using the member variables of P. Finally, for P resource, I don't want to copy over P's P resource. I could, but that's the problem that got us here, right? This is what the compiler generated for me automatically. I need to do something better. In fact, what I need to do is make my own resource up on the free store and have a different pointer that points to that different resource on the free store. Now that different resource can have the same values in it. So what I'm going to initialize this to is a new resource. And remember, it takes a string. I'm going to get the string by calling old P's, P resources, get name. So this copy constructor will just bitwise copy over the other three member variables. They're harmless, they're just strings and numbers. And for P resource, I'm going to ask the old P resource for its name and pass that in when constructing a brand new P resource of my own. Okay, let's give it a whirl. You can see that we are paired up nice and neat. Constructing, destructing. Two constructings, two destructings. Everything's in balance. There's no leak. We're not blowing up. So we got through this person choosing to construct a fresh person object from the person object we already had. That's not the only kind of copying that happens. There's also what's called the copy assignment. So if I take my existing fully constructed Kate, which has a resource, and assign it to Kate 2, which is also fully constructed and has a resource, the copy constructor is not what makes this happen. What makes this happen is the assignment operator. That's an overloaded operator, just like operator less than, or operator greater than, or operator plus equal, and the other operators we've talked about. And that, by default, this does a bitwise copy. And I guess you know what that means. It'll copy the pointer over, and when they go out of scope, they'll both have the same pointer, and we'll go boom. Just like that. So in order to protect against this behavior, we have to write an overload of assignment operator. I'll put that down here with the other operators. And the signature, rather like the signature of the copy constructor, it's not yours to choose. This is the signature of an assignment operator. It returns a person reference. That's so you can write x equals y equals z. And its name is operator equals. And it takes a const person reference p. Now let's implement it. I need to get the pieces over, and this is a handy way to do it. I can't use the initializer syntax in a operator overload the way I can in a constructor, but I can just reduce my typing this way. Here I'm copying the three member variables over, p.firstname, p.lastname, p.arbitrary number being copied into the appropriate member variables here, and I can new up a p-resource. But there's something I have to do first. In the case where we were using the copy constructor here, Kate 2 was not already constructed and obviously didn't have a p-resource. But here, where we're going in the other direction, Kate has a p-resource that's pointing to something on the free store. And if I wipe that value of p-resource out, putting in the pointer I get from this second call to new, I'm never going to free the old stuff. So before I new up something to put into p-resource, I gotta delete what is already in there. And again, remember, if it was null pointer, that's fine, that's harmless. Almost forgot. We have to return something, and the equals operator always returns star this. We've come all this way and never talked about this yet. This is a pointer that all member functions have secretly available, but because we haven't been living a very pointery life, we haven't used it yet. That represents the object itself. When this line of code runs, Kate equals Kate 2, this will point to Kate. When Kate.setFirstName runs, this will point to Kate. And when Kate.AddResource runs, it will point to Kate. If somebody called Kate2.setName, this would point to Kate2 during that execution of setName. It's in fact the mechanism by which member functions can get to the right member variable. This is a pointer. We don't return a pointer. We return a reference. So we dereference it with star. Star this. That's what you should return from an operator equals. Now let's run it. We have 4 pairs and they match up. We construct and destruct here. Then we have 2 constructs, 1 destruct, so a net of 1, another construct, so for a net of 2, and then 2 destructs. No leaks, no booms. We have finally constructed a fully robust person class. Because person had a meaningful destructor, we had to write a meaningful copy constructor and a meaningful operator equals or assignment operator, 2 names for the same thing. And I will not deny to you, this is totally